this is I've included a bit of recent research data in here, but it's generally an educational talk about PHIP at low magnetic field. So that's PHIP, that's parahydrogen-induced polarization. And we're not going to start the story at the beginning. There's some assumed knowledge for this webinar, so I'll quickly go through those points. So this knowledge is essentially assumed for the talk, and those points are that the hydrogen molecule has different spin isomers, so the nuclear spins can exist in different states, and parahydrogen is the singlet state of the hydrogen molecule. We also have orthohydrogen, which correspond to the 3 triplet states. We know that we can enrich parahydrogen by simply cooling down hydrogen gas on a suitable catalyst. You come down to low temperatures, a few tens of Kelvin gives essentially 100% para enrichment. And we already know that once you remove the hydrogen from the catalyst, it can be stored in bottles for days. And here's a nice plot showing that from Fro and Ellerman's recent paper, where the lifetime of parahydrogen is many days in an aluminium canister. We also know that the singlet state in the hydrogen molecule is what we call NMR silent, because these singlet triplet transitions are forbidden. So if we just measured parahydrogen gas, we would see no NMR signal. But if we measure normal hydrogen gas, where 75% of the population's within the triplet manifold, we can see these transitions. So parahydrogen itself is NMR silent, but that brings us to the final point, which is we know that if we react parahydrogen with other molecules, we are bringing these 2 protons into a molecule, and they are in this singlet state. And this is essentially a hyperpolarized state. And after hydrogenating molecules, we are interested in things like polarization transfer to other nuclei, or measuring the hyperpolarized hydrogens themselves. Okay, and here I've just outlined potential steps in a PHIP experiment. So the first thing is we convert our hydrogen into parahydrogen, and we introduce the parahydrogen into a sample. And normally this means bubbling the parahydrogen through a liquid. The parahydrogen then reacts or interacts with some other molecule, and that would be this step here. And then we have this important step of polarization transfer, and this is what I'll talk about mostly today. And so this is the step where we would want to convert the proton singlet order into magnetization of another nucleus. And then we might go on to do things like purify the sample if we wanted to do some sort of in vivo imaging with the molecule, or apply the molecule in other systems. And the final part of the assumed knowledge is about different magnetic field regimes. So I've taken this image from a recent review article about zero field NMR, and we define 4 different field regimes. And actually, so zero field is not really relevant for this talk, but so we define these field regime boundaries by the physical constants in the molecule. So if we imagine a molecule where we've got, let's say, 2 protons and they have a chemical shift difference and a carbon-13, so we have 2 different nucleus species, and we've got 2 protons that have a chemical shift difference, and we have J couplings between the spins. Well, then we can define these boundary conditions where our high field regime is essentially where the magnetic field's high enough that the chemical shift differences between nuclear spins of the same isotopic species is larger than the J coupling between them. And for a small molecule where you've got ppm chemical shift differences between protons, that field would be of the order of a few millitesla normally. We then have the boundary between the low field regime and the ultra-low field regime. And this boundary condition is where J couplings between spins of different isotopic species are the same order of magnitude as the Larmor frequency differences. So if we're thinking about proton-carbon, and our J couplings are typically of the order of, hertz or tens of hertz or up to a few hundred hertz, this boundary condition is occurs at a few hundred nanotesla normally. Oh yeah, right, we have some example values here. Okay, and we have this final field regime, zero field, where in this interesting regime, we define this where the spins, their characteristic relaxation time, and that might be T1 or T2, their characteristic relaxation time is of the same order of magnitude as the precession frequency. Okay, but this isn't really relevant for this talk. All right, so let's paint a picture then of we'll build up complexity in this in a PHIP system. So the first thing we can have is just a hydrogen molecule, and our Hamiltonian, we have a J coupling between the two hydrogens, and we have this Zeeman term if the hydrogen's in a magnetic field. And so in this case, we have 4 states that can be populated. And if our initial density operator corresponds to just thermal equilibrium magnetization in a magnetic field, we have some distribution of population between the states. And if we were to take an NMR spectrum, we see the hydrogens at a single resonance frequency. We have a single line in the spectrum. Okay, so our initial density operator in that case corresponds to a term like this, where we have these IZ operators and this value P, which is some very small number because our polarization is incredibly low in this case if the spins are polarized in a magnetic field. So if we increase the complexity of the system a bit, we now imagine that let's say we react our hydrogen with some molecule, and now the protons have a chemical shift difference in the target molecule. We'll neglect the J coupling term here between them. We'll just say we have 2 hydrogens with a chemical shift difference. Well, now the situation changes. So now the 2 hydrogens have a different precession frequency because we've introduced this chemical shift term. And so the eigenbasis is different. So now we would describe the spins in this Zeeman basis, where we can write states such as alpha, beta. And in a spectrum of this molecule, we would have 2 peaks corresponding to the 2 precession frequencies for the hydrogens. Of course, we know this isn't very realistic. In this case, we would have a J coupling between the 2 hydrogens. And so if we introduce that J coupling again, that would cause a line splitting. That would shift these energy levels. And so by reintroducing that term, we have our expected spectrum here for this molecule. Okay. Now, the situation with parahydrogen is very different. So if we now look again at just the hydrogen molecule, so we have the same Hamiltonian as before, but now our initial density operator is different. It takes this form, and this corresponds to 100% of the population being in the singlet state. And we know that the singlet triplet transitions are forbidden. And so if we take an NMR spectrum of the hydrogen molecule, we see nothing. That's why we say it's NMR silent. And so what we need to do is we need to react the hydrogens with another molecule and break the symmetry so that the singlet order is the state is changed and it becomes observable. And so if we imagine doing that, we react the hydrogen with a molecule, and now we've introduced our chemical shift difference term. This breaks the equivalence of the 2 hydrogens. And in this case, we have a change then of the density operator, and it changes from this form into what we would call, it's referred to as ZZ spin order. Okay, and what's going on there is, well, this is our initial density operator written in matrix form. So we have all of our population occupying the singlet state. But as the hydrogen molecule reacts, the state basis changes. And so we need to project the initial density operator onto a new eigenbasis, which is, well, to a good approximation, the Zeeman basis. And this is a good approximation if the chemical shift difference between the 2 hydrogens is much larger than the J coupling between them. Okay, and in this case, what happens is, so the state basis changes, and we have half of our population in this beta alpha state and half in alpha beta, and a coherence between those 2. And now the coherence will begin to evolve. But because this is a chemical reaction occurring over time, the molecules are hydrogenated at different points in time. And so these coherences, they pick up a phase, and they essentially get washed out as this reaction continues. So we're essentially just averaging, we're taking the time average of these oscillating coherences, and they average to 0. And so what we're left with is the density operator of this form, where all of our population is split between these two states. And as I say, this is what we refer to as ZZ spin order. And this now, if we do a NMR experiment on this molecule in this state, we see a very different spectral pattern. And this is a PASADENA experiment, and we see a characteristic up, down spectral lines. And that corresponds to these single quantum coherences that we excite with the pulse. Okay, so for the same molecule, we have two very different spectra there. So if we take a spectra at thermal equilibrium, we have our in-phase lines that we expect. And if we do this experiment with parahydrogen, we have a completely different spectral pattern because we've selectively populated these two states. And what's not shown here is that this density operator does not contain this P term, this very, very small polarization. And so, of course, these lines would be enormously enhanced. I'll note that when we excite these transitions, because we start with this this ZZ term, we don't use a pi/2 pulse because that would excite a double quantum coherence, which is not observable. So we use a pi/4 pulse, and that excites these, that creates these terms, and these ones are observable. Okay, so that's the two-spin system case, and we can have a similar effect in three-spin systems, as shown in a nice paper by Andrei Pravdivstev, where we start with a molecule like this, and in this case we're interested in this carbon 1 here. So we hydrogenate this triple bond, and now we have our parahydrogen protons, and one of them's directly bound to the carbon. Okay, so there might be, the protons are almost chemically equivalent, except for a small isotope shift. But they have almost identical chemical shift, but they have a very large difference in J coupling to this carbon-13. And that large difference in J coupling acts in a similar way. That also strongly breaks the equivalence between the hydrogens. And so you see this characteristic up, down line pattern. Okay, so the relevant parameter there then is as a mixing angle. And this mixing angle theta is, well, it's down here. That's given by this term, where the two relevant parameters are the chemical shift difference between the protons, or we may, in the case seen on the previous slide, this would actually be the J coupling difference to a third nucleus, and the J coupling between the two protons. So we see that when the J coupling between the two hydrogens dominates, then we're in what we call the near equivalence regime. And the states that would describe the system are very close to the singlet triplet states. And then if this chemical shift difference term is introduced and is much larger than the proton-proton J coupling, then we're in the far from magnetic equivalence regime, and our states would be closer to these Zeeman states. Okay, and that's shown here actually this is shown on this eigenvalues plot. So you can imagine actually, and this is going to become very relevant later on in the talk, if we can neglect this case. So we're in this case here where the chemical shift difference, that there is a chemical shift difference between the two protons, and as we increase magnetic field, that means that these states will diverge. So if we're at zero magnetic field, there is of course no chemical shift difference between them, and we're in our near equivalence regime. And at zero magnetic field, then the protons become indistinguishable, and so of course the singlet triplet states would describe the system. And as we increase magnetic field, we increase the relative size of the chemical shift difference, and at some point you see these states diverging, and we've entered this Zeeman regime. Okay, so let's take a look again then at what's going on. This is kind of revisiting that PASADENA experiment case. So we're hydrogenating a molecule with our two protons, and we've got these terms where we have the J coupling, the chemical shift difference, and I've put in a couple of simulations here. So let's say that the chemical shift difference is 10 times larger than the J coupling between the protons. So we're far from equivalence. So in this case, what do we have? We have our Hamiltonian, and it's structured like this. So if we write the Hamiltonian in this matrix form, we have these J coupling terms on the diagonal, and this chemical shift difference term that connects S0, the states S0 and T0. Okay, but if this term is 10 times larger than the J couplings, then these off-diagonal elements completely dominate, and so this is not the eigenbasis of the system. And we will see immediate evolution of a density operator where we have single order. And that's what we saw in the PASADENA experiment. So if we start with full population in the singlet state, well, we have these very large terms that connect S0 and T0 on the off-diagonal. And so we'll see immediate evolution between the singlet state and the triplet zero state. Well, that's represented here in this, I'll have to, oh yeah, well, it's just shown here in a simple animation. And then that's plotted down here. So we see that if we hydrogenate a molecule, we start with the protons are initially in a singlet state, and then that evolves over time. So after some time, the probability of finding those protons in the singlet state has decreased. Okay. If we're in the near equivalence regime, so now we imagine doing a similar experiment. We've hydrogenated a molecule. But now the J coupling is 10 times larger than the chemical shift difference. So we draw a molecule like this, where we imagine these are different R groups, and there's a small chemical shift difference between the protons. Well, in that case, when we look at our Hamiltonian, now these diagonal terms are an order of magnitude larger than the off-diagonal elements. And so this the difference here between the S0 and T0 state energies is very large compared to these terms. And so this is close to an eigenbasis. And what we see is that after hydrogenating a single molecule, we do have evolution of the state, but it's small. And that's just shown in this animation here. So our state will just evolve. It evolves, but it never, there's very little mixing between S0 and T0. Okay, so in this case, we see that we hydrogenate a molecule and we essentially keep the single order between the two protons. And if we want to convert that single order into some observable state, then we're going to need to use some sort of pulse sequence or some field sequence. Okay, so that's what's shown here. So if we allow the singlet state to evolve for some time, and then we apply a pi pulse, we invert the phase of the singlet zero triplet zero coherence, and we can repeat this process with a defined tau, and that will allow us. I'll play this animation here. That allows us to convert between single order and triplet order. So we see this S0 T0 coherence evolves, and every time it oscillates by half a period, we apply a pi pulse to the protons, and that inverts the phase, and the evolution begins again. And in this way, we can essentially bring the state from its initial state down into to full population of T0. Okay, so that 3D animation is shown on this two-dimensional plot, where these are just the probabilities of finding the state, finding the system in a given state. Okay, and yeah, so what's written down here is that these numbers here, tau and n, these are essentially given by the J coupling and the chemical shift difference in the molecule. All right, so that can be that sort of element, this spin echo element, can be incorporated into sequences to do singlet magnetization conversion. So I've taken this from this paper from 2010 by Giuseppe Paleo. Let me go back to my pointer, where we can have these sequences that will create some defined evolution of the spin system. Okay, so in this case, what do? So we've hydrogenated our molecule. We start out in a singlet state, and now we want to create proton magnetization from that. So the first thing we do is we apply this spin echo train n times. And so our population evolves from the singlet order. And what we do is we reach the halfway point where we've got half the population in the singlet state and half in the triplet zero state, and a coherence between the two. And at that point here, we wait for an additional tau period, and that lets this coherence pick up a pi/2 phase shift. And then we apply a 90 pulse. And that's going to exchange the population and coherence from triplet 0 to triplet plus and triplet minus. Okay, and from this state here, we then apply a second spin echo train with twice the number of elements. And then that will fully exchange the singlet population and coherences to the outer triplet states with T0. And we reach this state here. And this state would actually, this corresponds to proton magnetization in the transverse plane. And so what we do is we apply a final 90-degree pulse, and that rotates our magnetization to the z-axis. So you see that we've essentially incorporated these elements, these spin echo elements, into a sequence, and we've converted from the singlet state into a state of proton magnetization. Okay, so that was like what we could call a hard pulse method. I mean, this can be done at high magnetic field, using by just pulsing on the sample using conventional hard pulses. But a different approach that was published in 2013 is what we could call a soft pulse approach, and this method works a little bit differently. So we have a similar system. We've got two protons, and they have some small chemical shift difference. And now we're going to introduce a transverse magnetic field, and that's called the slick pulse, a spin lock induced crossing pulse. So this nu here is a weak magnetic field that we can apply in the x-axis for a defined time tau. So if we look at the Hamiltonian, it takes this form. So we're familiar with these terms. We know we have our J couplings on the diagonal and our chemical shift difference connecting the S0 and T0 states. And as we switch on this weak pulse in the x-axis, that introduces these terms here that connect the states in the triplet manifold. Now, if we change the state basis, so we rotate our the states where we're representing this Hamiltonian, so it's the same Hamiltonian represented in a rotated state basis, we see more clearly the effect of this X magnetic field, nu, and that is to affect these states here, so that by choosing a particular value of nu, in this case setting it to equal the J coupling, that means that you're applying a magnetic field so that the protons are nutating at the J coupling frequency, so a very, very weak magnetic field. We see that we can choose a value of nu so that these diagonal elements, in this case, this T minus element is equal to the S0 element. And at that point, if we've chosen that value of nu so that these terms are equivalent, we have evolution between those two states. So our population that was in this singlet state will begin to evolve into T minus. And that's shown down here in this plot. So we start out with 100% population in the S0 state. And as we turn on the slick pulse, that population decreases, and the population of T minus will increase. Okay, so what we've done is we've applied this field to equilibrate the energies of these two states so that the off-diagonal elements allow evolution between populations of those states. Okay, so what's going on there? A nice way to represent this is using an eigenvalues plot. And using this, we're looking at what's called a level anti-crossing here. So what's plotted here are the state energies of these rotated states for different spin lock amplitudes. Okay, so our amplitude nu here, this is in hertz, and again this corresponds to how fast the protons would be nutating under this X magnetic field that we're applying with the NMR coil. So very, very small values, of course. I mean, we're used to, hard pulse methods where the spins are normally rotating at tens of kilohertz. But here we're just talking about 10 hertz or so. Okay, so what we see though is that if this X field is set to 0 amplitude, well then we have our expected state energies. We have our singlet state at lower energy than the 3 triplet states, and as we increase this this applied field, we see these states approach each other in energy, and then they have this avoided crossing or level anti-crossing. And so I'll speak a little bit more about this in the next few slides, but essentially by setting our transverse field at this amplitude and sitting at this point, we drive coherent evolution between the populations of these two states. Okay, so that's what I've talked about so far then has been 2 spin systems. But in many applications, many real cases, we're interested in 3 spin systems. Oh, okay, a nice example of that shown here. So, you know, if we want to polarize a molecule such as pyruvate for in vivo imaging, and we want to polarize the carbon-13, then what we're doing is we hydrogenate a molecule and we need to transfer the proton polarization to this 3rd nucleus. And in this case, we'll neglect the other nuclei in the molecule. So we transfer the polarization to the 3rd nucleus, and then we would cleave off our pyruvate and collect this for use. So for the next section of the talk, I'll talk about 3 spin systems at low field. So we're going to introduce this difference in J coupling to a 3rd nucleus. But we're going to be talking about the low field regime. So chemical shift differences between these protons are suppressed. We can neglect those terms. So the Hamiltonian will have a structure like this. So our Hamiltonian has these Larmor frequency terms for the protons and the 3rd spin. And then it has J coupling terms between the 3 spins. Okay. And I've added one more point here. I say we're often interested in the near equivalence regime, and that means that the 2 protons are near to magnetic equivalence, and that occurs when the J coupling between these is much larger than the J couplings to the 3rd nucleus. Okay, so yeah, let's take a real example then. So this molecule is fumarate. And we can produce this by reaction with parahydrogen. And then here are the J couplings. So we've got this proton-proton coupling of about 16 hertz, and these proton-carbon couplings are smaller than that. And we are in the near equivalence regime with this molecule. And so the state basis is approximately described by taking this Kronecker product between the proton singlet triplet states and the Zeeman states for the carbon spin. And so we end up with 8 states, and they have, we have these states. So taking one example, T plus beta, this means the protons are in the triplet plus state, and the carbon's in the beta state. Okay, and in this case, we have, if we come over to this eigenvalues plot, so what we're plotting here then is the energies of those 8 states for different magnetic fields. And we see that at 0 magnetic field, the two states that correspond to proton singlet order are the lowest in energy, and the other states are higher in energy. And as we increase the magnetic field, the state energies diverge, and we have this important level anti-crossing here, this avoided crossing between 2 of the states. And those 2 states, we can follow the lines, that's singlet alpha and triplet plus beta. So these 2 states, there is an avoided crossing between them. And that's because if we look at the Hamiltonian structure, if we write the Hamiltonian in this singlet triplet Z state basis, we can find those states. We have singlet alpha and triplet plus beta. And we see that there's a point where these diagonal elements can be equilibrated in energy. And the off-diagonal elements, well, they lead to this avoided crossing between those 2 states. And that means that we can have population evolution between these states. So we will be able to use this to transfer population from the singlet alpha state to triplet plus beta. I've written down here this matching field condition here, this is approximate. And you see this occurs at a field value of a few hundred nanotesla. And this is essentially that field boundary condition that I mentioned back in the first slide, where I talked about this. We have this low field regime and ultra low field regime. Well, here we're down at these ultra low magnetic fields. Okay, so if we then, so we can look at an experiment, and this was first shown. This type of experiment was first shown back in 2004, where this molecule here was hydrogenated, so the hydrogen's incorporated, and then and that was done in a simple apparatus like this, and by bringing the sample into this low field chamber in a magnetic shield and controlling the magnetic field with a coil. These field changes can be implemented, and so here's a diagram of how the experiment can look. We do the bubbling to hydrogenate the molecule at some reasonably high field, and then drop the magnetic field close to zero, and then ramp it up slowly. Okay, so and what happens when we do that? So we start out with all of our population in these two singlet states. Okay, well, we know that because if we've hydrogenated the molecule like this with parahydrogen, we know that the two hydrogens are in a singlet state. And so our populated state should be singlet alpha and singlet beta. And essentially at 50-50 population because the carbon spin is not polarized. So if we have all of our population split equally between these two states, and then we rapidly drop the magnetic field to zero, well, the populations remain in those states, and so our populations are here. And then by ramping up the magnetic field slowly, adiabatically, what we're doing is we're shuttling the populations through this avoided crossing. And if it's done adiabatically, and that means that the increase in magnetic field is very slow compared to the inverse of the energy difference between the states at this level anti-crossing, then our populations will evolve along these lines, and we end up with populations in the states singlet beta and triplet plus beta. And so you see what's happened there is we've lost some amount of proton singlet order, but we've now fully polarized the carbon because the population is split between these two states, which both have the carbon in the beta state. Okay, so well, here's then a real example of this. So here's what the experimental apparatus can look like. We have this magnetic shield. So our sample can be held in an NMR tube inside the magnetic shield, and we have coils around the sample. And those coils, like pulse field coils, allow us to apply well-defined magnetic fields. Okay, so we can bubble parahydrogen through the sample to hydrogenate the molecule. All right, and that's what happens here in this step. We hydrogenate the molecule and we produce fumarate. And then we can apply this, this magnetic field sequence to convert the proton singlet order into carbon magnetization. And that's shown in the sequence here. Okay, so we hydrogenate the sample at 2 microtesla, drop the field down, and then ramp it up slowly. And then we will shuttle the sample, and that takes about 3 seconds. We shuttle the sample through here into a spin-solve high field NMR magnet. This is a benchtop system, and we detect the signal. Okay, so if we do that experiment, well, here's an example of one of the carbon spectra in green. Okay, so we collect an enormously enhanced carbon spectrum. So the signal enhancements of the order of 10 to the 5. So we have some enormous carbon signal, and we can compare that to the sample at thermal equilibrium, which gives a very, very small signal. So we think, okay, great, well, our sequence here has worked. And then we can investigate a sequence like this. So I mentioned before that the rate that we increase the magnetic field, and that corresponds, if I just jump back, that corresponds to the rate that the system passes through this avoided crossing. This is very important because if we do that too quickly, then the spin system doesn't have time to evolve, and we will not populate this state. But if we do this too slowly, then of course the spins are relaxing over time. So then that's shown on the plot here. So this is the sweep duration in seconds. So the black points show this linear magnetic field ramp. And we see that if the duration of that field ramp is close to 0 seconds, then we have very, very low carbon polarization. And as we increase the time, we hit some sweet spot at around 3 or 4 seconds where we maximize the carbon polarization. And as the sweep becomes longer, then relaxation starts to play a more important role, and we lose carbon polarization. Okay, but if we can be a little bit more clever about that, and we can do a constant adiabaticity field ramp. And that means that we're only slow in the region of the avoided crossing. So we're only slow in this region here. And it turns out this is a bit more effective for generating polarization. So the sweep can be much shorter in this case. Okay, so one challenge though, I just bring up a few plots here from different papers where these sort of magnetic field regimes are being optimized for different experiments. One problem that we face is that it's not possible to detect while we're driving the spin system. Okay, so we can apply these sort of, we're interested in this part here, this polarization transfer step. But if we want to collect this sort of data, we repeat the experiment many, many times, and we're collecting single carbon spectra each time. And that's because we're not able to observe what happens during these magnetic field sequences. And the reason for that is because, so in most cases, you've got you've got a detector, whether that's a magnetometer or an NMR coil. And when you're applying a magnetic field to your sample, so you're pulsing on the spins, you saturate the detector. So at high field, this would correspond to the idea that you need, if you're pulsing, you then need to switch off the pulse and wait for a short duration, and then you can acquire a signal from the sample. But if you were to detect while pulsing, of course, the coil would be completely saturated. And that's true as well for these magnetometers for low field NMR. But back in 2004, this paper was published from the Pines lab, where they showed that you can use a piercing solenoid. So this is a solenoid that passes the whole way through a magnetic shield. So you have a sample inside the solenoid. And in this way, you can apply magnetic fields with the solenoid to the sample, but the magnetic field lines from the solenoid will pass through the shielding and around. And so in this way, you can apply a field to the sample, but not at the position of the magnetometers. Okay, and so a couple of years ago now, when I was in Barcelona, I worked with Michael Taylor at ICFO on this low field NMR project, where we used this method to study polarization transfer in real time. And I just give a quick shout out to the NMR Arduino that we were using. This is a low field NMR system essentially in a card. So we use this to apply digital and analog outputs to control the coils and valves. And so I'll say a few words about what we were doing in those experiments. So here's a schematic of the experimental setup then. So we have our magnetic shield, the NMR sample inside this solenoid, and we have a sensitive magnetometer just outside the solenoid and next to the sample. And so what it means is we can apply magnetic fields through the solenoid that will affect the sample, but they have a very minimal effect on the magnetometer. In fact, the field inside the solenoid is about 1,000 times larger than the field just outside. Okay, and what that means is we can do these experiments where we do our hydrogenation and we produce our fumarate with the protons in a singlet state. And then what we're interested in is these polarization transfer mechanisms where we drop the field close to 0 and ramp up the field. And our fields are of the order of a few microtesla. And that means that the magnetometer is seeing a residual field from the solenoid of just a few nanotesla. And that's okay. It's still sensitive and it can still operate with a few nanotesla field applied. And so what we do in these experiments is we hydrogenate to produce fumarate. The protons are in a singlet state. And I've said before, this is essentially a non-magnetic state that we can't observe. And so we apply pi pulses and we try to detect magnetization, and we see essentially nothing here in red. And then we drop the magnetic field close to 0 and ramp it up. And we see that as we pass through this 400 nanotesla level anti-crossing field, the sample's magnetization jumps up. And that's because, well, both the carbon and the proton are polarized. In fact, what we're seeing is predominantly the proton magnetization, because the protons went from a singlet state into this T plus state at 50% population. And then we can apply these pi pulses and toggle the magnetization up and down. And so we start with a very, very small or almost unobservable signal. And applying this sweep, we see in real time how the magnetization changes. And then we see, of course, we do have this large magnetization now that can be flipped up and down. Okay, so we applied this sort of experiment in a few different ways. We thought this is exciting because essentially now we can actually see the dynamics of the sample's magnetization in real time. So that case here is shown for fumarate, and we do a similar experiment with a similar molecule, and this is maleic acid. And for this molecule, the J couplings are different, and we see completely different dynamics as we ramp up the field. So it's the same experiment. We drop the field to 0, ramp it up to 2 microtesla, and we track the magnetization of the molecule. And we see for maleic acid, we get this very strange looking large oscillations, but we end up at a similar point. And so you see that if we were doing this in the normal way, where we just apply we apply a field sweep and then we take the sample out and we measure it at high field, we would detect some large magnetization, but we'd have missed all of these interesting dynamics. And so these were for linear field sweeps. And you can see very clearly here for fumarate that you get this sudden jump in the magnetization at about 400 nanotesla. But we can do this with constant adiabaticity field sweeps as well. So in this case, we quickly jump up to close to 400 nanotesla and then pass through that important regime, and then we jump up again. And in this case, we see a much more sort of what looks like a much more linear increase in the magnetization. A couple of other experiments shown here where we do field sweeps through 0. So this corresponds to inverting the applied magnetic field. And there we see, well, again, very different sort of dynamics, where we see the magnetization builds up in a negative sense and then flips. Yeah, okay, I think I'll carry on now. So because these are adiabatic field changes, we're adiabatically ramping up the field to induce that transition. It means it's a reversible process. So this is our applied magnetic field going from 2 microtesla, we go down to 0, we ramp up, and we can ramp up and down we can do this continuously, and we can measure the magnetization from a sample, and the sample's magnetization essentially increases, decreases, and it does this. The fidelity is reasonably high for this sort of experiment. We do this many times over about 10 seconds. Of course, we're losing signal due to relaxation of the spins. And so that is then shown here. So what we have then, we have a load of different experiments here. So we've got adiabatic field sweep duration. So here it's 0.5 seconds. And in this experiment is 1 second. Okay, so we don't necessarily expect too much difference between these experiments. Okay, so, and we have different carbon labeling fractions. So I think maybe for this, we can just focus on this case here. So 2.2% carbon-13 in fumarate. So this is at natural abundance. We see that if we have this half a second field sweep, we just generate magnetization. It goes back to 0 as we reverse the sweep. And this happens many times with reasonably high fidelity. If we change the sweep duration to 1 second, we see what looks like very, very different dynamics. It looks like it's becoming somewhat chaotic. And it basically took a few simulations to work out what's going on here. It turns out this just happens to be a length of time where you have some slight evolution of coherences that you're generating by imperfections in this field ramp. I think actually I have a, okay, yeah, there's a, oh, well, okay, well, I won't be able to show you that, unfortunately. The GIF is not playing. But essentially, we see that as you ramp up the magnetic field and then back down again, you have this this evolution on a Bloch sphere, in this case, where we're looking at the state of the system evolving from, you know, S0 alpha to T plus beta. And it just happens that at this particular duration, we have what looks like very chaotic dynamics. And that can be remedied by just changing the duration slightly. I think what's not shown here is that you know, the change can be very subtle. You can just shift this time by about 50 milliseconds and you get completely different dynamics. Okay, I think I will pass over this this part about distant dipolar fields just in the interest of time, and finish up by talking about ways to prevent loss of singlet polarization in experiments. So a lot of the time, what I've just talked about is the low field regime, where we don't have any chemical shift difference between the protons because we're at low magnetic field when we do the hydrogenation. And so we didn't really have to worry about losing singlet polarization in those cases. But let's see now. We can talk a little bit more about that. So if we're doing reactions at high field, and we do have chemical shift differences, this leads to loss of polarization. We've seen that already, because the singlet state's not an eigenstate if these terms are non-zero. So we can suppress this by just working at low field, or by spin locking. What we can do is, if we're doing these reactions at high field, we can apply strong transverse magnetic fields and spin lock the protons. So if we look at the Hamiltonian under spin locking, well, this is very similar to our slick pulse, except now these terms nu are much larger. They're not some small value like 10 hertz, but we can just apply a strong transverse field. So if we write this Hamiltonian in the dressed state basis, well, we've seen this on a previous slide, except now what we're doing is we're setting nu to a very large value. So we're disconnecting the states from each other. And so if this is some very large value, this singlet state is no longer connected to any of the other states. And so population will remain in the singlet state. We're essentially, we're ensuring that the singlet state is close to an eigenstate by applying this spin locking. And that was shown by, in this paper from 2020 by Larry Nastagis. This was shown in a nice way where they do a geminal hydrogenation to produce this molecule with the 2 parahydrogen protons in these geminal positions. And if they do this, they can do this reaction and then read out the signal. And they see that if they're not spin locking, the signal quickly decays. Relatively quickly, you lose the proton magnetization. But if you apply spin locking, and the reason that you relatively quickly lose the polarization is because these protons do have a chemical shift difference. But if you apply spin locking, you lock them in a singlet state, and you can generate much larger magnetizations that persist for a longer time. And that's shown here. So the protons have a very short T1, but the singlet lifetime is about a minute. Okay, and finally, I wanted to talk about this paper from Alistair Marshall and Stefan Knecht from 2023, because I think this paper is a really nice example. So this is in the Journal of Physical Chemistry Letters, a really nice example of showing the importance of working at low field and spin locking to suppress singlet triplet mixing. So what I've just talked about is chemical shift differences between the protons that can lead to singlet triplet mixing. But another thing that can happen is we can have inequivalent J couplings on the catalyst, for example, so during the hydrogenation. And if we have inequivalent J couplings, this can also lead to singlet triplet mixing and loss of polarization. So what they showed in this work is, well, it showed a few different things. So the first thing to show is the importance here of introducing decoupling. So if we take this reaction as an example, they're reacting this precursor molecule to form dimethyl malleate. And you can do this at low magnetic field. So this corresponds to these green bars here. So if you just apply low field polarization transfer, you get, well, about 23% polarization. If you do this reaction and you apply decoupling, you get more than double the polarization. And that's presumably because you're suppressing some singlet triplet mixing that's occurring on the catalyst. I mean, these protons are almost chemically equivalent in this in the product molecule. So it's almost certainly on the catalyst that you're losing polarization. And this is obviously an enormous difference. And they see the same for this molecule here, the deuterated form. So this shows a clear benefit of applying decoupling while you're doing your PHIP reaction. So by applying this decoupling field or spin locking field, you're maintaining the proton singlet state through the reaction, and that helps preserve the singlet order if there's some chemical shift difference or inequivalence in J couplings to other nuclei. What's also shown, though, is they also do experiments at very low magnetic field, so ultralow field, and these are shown in orange. This is for B0 magnetic field sweeps. And in this case, so this would correspond to what I showed before, where you drop the field close to 0 and ramp it up. So in some cases, that's just about as effective as a low field polarization transfer. So for fumarate shown here, it looks like it makes no difference whether you do ultra low field transfer or transfer at low field with some pulse sequence. But there are other cases. So you'll notice that in all of these cases where there's deuterium in the molecule, in those cases, so we can look at this example here, you have much lower polarization when you do a B0 sweep. And that's because when you go to ultra-low magnetic fields, all of the spins become strongly coupled. You've suppressed the Larmor frequency differences. So if you have some nuclei that relax quickly, like deuterium, this can be this acts as a relaxation sink for your polarization. And so you can see, for this dimethyl malleate, if we compare the B0 sweep with the B1 sweep, we have similar polarization for both cases. But if we look at the same molecule, but we've deuterated those methyl groups, then the polarization is significantly lower if we use a B0 sweep. So then this is my last slide, where I just show then a comparison between working in the different field regimes. So, well, this sort of brings it all together. So we have the high field regime, where you do your PHIP experiments in a high field magnet, and you're using a coil to pulse on the sample. We have the ultra-low field regime, which is a lot of what I showed today, where we're changing the B0 magnetic field around the sample, and it takes values of a few microtesla. And then we have this regime in between, the low field regime, where, that's sort of shown in this setup here, where you've got a B0 coil, your sample's in a shield, and you're applying a field of some tens or hundreds of microtesla. So you're at low field. So you don't have chemical shift differences between spins of the same isotopic species. And you use another coil, a B1 coil, to apply pulses. Okay, so then, we can just make a sort of a comparison of the advantages and disadvantages of these regimes. So in the high field regime, so one key advantage is that because your spins have large Larmor frequency differences and chemical shift differences, you can individually address the spins. You can pulse at particular chemical shifts and address spins individually. You can do this at low field for different isotopes. So you can address protons, carbon, or nitrogen-15 separately. But of course, you've suppressed chemical shift differences here. And in an ultra-low field regime, you can't do any of that because all the spin, you've suppressed all Larmor frequency differences. The advantage of high field as well is that you don't have strong coupling to relaxation sinks, and that's also true at low field. And that's a disadvantage of ultra-low field work. So if you've got deuterium or nitrogen-14 in the molecule, you can quickly lose polarization. And the final advantage of working at high field is there are many cases where you might be doing in situ hyperpolarization, and you can immediately detect your polarized spins. So for some applications, clearly this might be really, really important. And that's a disadvantage of working at low field or ultra low field. If you want to detect in a high field system, you need some sort of sample transport. But then there are some disadvantages of working at high field, and a clear one is that you're only addressing a small fraction of the sample that's within the coil. Whereas for these two regimes, it's easy to just have a large coil that addresses the whole sample. At high field, it also maximizes proton chemical shift differences. So in a sense, you're maximizing the possibility for singlet triplet mixing, especially on the catalyst. And those are suppressed at low field and ultra low field. And then here we have the, if you're doing this at high field, then you need a high field NMR or MRI system with corresponding probes. But the hardware to work at low field and ultra low field is much simpler. You need a magnetic shield, a current driver, and some audio amplifier. I mean, the frequencies that are relevant for these regimes are hertz or kilohertz magnetic fields, and that's quite easy to generate with simple hardware. Okay, and so with that, I'll wrap up. I'd like to acknowledge all of these people who have contributed in different ways to the work that I showed here, and the people in my group who I've just established this hyperpolarization methods lab in Jülich, and these are the current group members. So it's been great working with them so far, and I'll say that we have master's and PhD positions available if anybody else is interested in joining the lab in Jülich. All right, thanks very much.
Thank you, James, for this very nice tutorial about parahydrogen hyperpolarization. I have 3 chapters of questions, but I will let the others ask their questions. So we already have one from Balvinder. He said he enjoyed your talk, and he wanted to ask about the time you invest in recording your experiments to obtain meaningful interpretation of the acquired data for 2-spin and 3-spin cases. And the second part of the question is, what are the possible direct applications you see for this setup? So the combination of low field and parahydrogen hyperpolarization.
Okay, yeah, let me just, now I've just opened up, and now I can see the questions right, yeah.
Yes.
Time invested in recording experimental run for meaningful interpretation of acquired data. Well, okay, yeah, so that's a good question. Let me just jump back then. Can you see the presentation, or is there the Q&A box in the middle?
No, we see your presentation.
Okay, great. Yeah, so yeah, time invested to collect data is yeah, that's a good question. I mean, you basically, you do a single experiment. Okay, so these experiments are relatively easy to do. I mean, you're bubbling hydrogen through a sample, you apply some magnetic field, and you detect a high field. So it might take a minute or so to do an experiment like that. And you're collecting some signal. So our signal to noise is very large. So in these sort of experiments, we're not typically signal averaging for any, we don't typically do that. So, I mean, to do experiments like this, I mean, if I understand the question properly, I can say that building this sort of apparatus is that can take some time, some days or weeks. But the experiments themselves are relatively fast. Having said that, if you're collecting all of these data points individually, well, that becomes quite time consuming. And then possible direct applications that I see for the setup. Well, yeah, I mean, one obvious application that I guess everybody is aware of, probably the key application, is to produce hyperpolarized metabolites for in vivo imaging. But with some of maybe there are some other applications in quantum information science, especially based on some of this work where we have good control over a 3-spin quantum system that has a very long lifetime of many seconds. So maybe there's some sort of applications there for quantum information science.
All right. Thank you. Another question from Mark. So he's asking what determines the minimum splitting, so J splitting, I think, at the anti-crossing point. Is this minimum splitting determining how slowly the anti-crossing region must be traversed?
Yeah, so I'll just jump back then. So this is, yeah, so here's like the level anti-crossing shown. Yeah, so this minimal splitting here, this is, maybe I can even go back another slide. So this minimal splitting here is given, I think it's twice the size of the Hamiltonian elements that connect those two states. So the states here are singlet, alpha, triplet plus beta. So if we look at the Hamiltonian in this matrix form, that's these two states here. And so these are the off-diagonal elements that connect them. So I think the splitting is twice the size of this off-diagonal element. And you're right, yeah, exactly. So that energy difference defines how fast you can traverse that level anti-crossing. It's defined by the Landau-Zeeman formula in this principle of adiabaticity.
Thank you. Another question from Bono. Said it was a very nice talk. So on slide 15-16, he was wondering why do you hydrogenate at 2 microtesla rather than at near zero magnetic field? And the second part of the question is relaxation too efficient at such low fields?
Yeah, that's a great question. That's a great question. It's yeah, the first thing is relaxation it's more likely to, the lower the magnetic field, the more efficient relaxation from paramagnetic species becomes. So if there's oxygen in the solution, oxygen is paramagnetic, and so relaxation would be faster. But to be honest, the real reason is that it's a cleaner way of doing the experiment, because at zero field, let me jump back. This level anti-crossing diagram is a little bit exaggerated, but at zero field, this eigenvalues plot is shown for this case of sort of extreme magnetic equivalence, where you've got 10 Hertz proton-proton coupling and a 1 Hertz difference in couplings to a third spin. And so in this case, you've got a really clean sort of, you've got one level anti-crossing here and sort of nothing around it. But in most real cases, we have these couplings are of a similar size to this proton-proton coupling. And that means, so that corresponds, so the difference in couplings here, the difference in these proton-carbon couplings is this off-diagonal element. And so if that's relatively large, as I just mentioned in the previous question, that means that the splitting between the lines in the level anti-crossing is large. And actually, I think I don't have a plot here to show it, but it basically means the level anti-crossing is quite big and it covers much of this field regime. So it's sort of a cleaner way to do the experiment to be up at a higher field where you're very far away from the level anti-crossings. I should also add there are more anti-crossings here very close to zero field that you can't really see in this diagram. But those are given by these terms here. So there are also terms that connect the triplet states. So there are also anti-crossings here. Yeah, so maybe that's something of an answer. It's like a cleaner way of doing the experiment. Okay. But I should say it's a good question, because absolutely, I believe that you could do the experiment hydrogenating at zero field, and I think it would essentially work similarly.
All right. Asif had a question. So you showed the effect of field and challenges associated with different regimes. How do you choose the optimal field for more general molecule, not necessarily metabolite? And are there hybrid systems that can switch between high and low field regimes?
Between high and low field? Not that I'm aware of. So, high field really means, in a high field system, you at least have like a benchtop NMR magnet. So you're at sort of at least a Tesla magnetic field if you imagine a high field experiment. So I'm not aware of any systems where you can sort of interchange between high field and low field, because high field requires like a very homogeneous high magnetic field and a coil, and in low field you need a completely different setup. It's, of course, there are many systems where you can sort of do low field and ultra low field experiments. That's shown here in this nice figure from Alistair's paper, where you've got a shield and you've got this B0 coil passing through, and you've got a B1 coil. So you can essentially, in this case, choose whether you want to just have some fixed B0 of maybe 50 microtesla, and then apply pulses with B1. So that would be a low field experiment. Or you can switch off the B1 coil and just vary B0 in some low current regime, and then you're working at essentially ultra low field. So these two are sort of relatively easy to combine in one experimental setup. And I think the first part of the question was about choosing optimal field regimes for different molecules or cases. Yeah, so yeah, I mean, it's a great question. It's basically, I guess that's sort of where we're at right now. It's people are interested in different systems and doing different things. Some people are using parahydrogen to do like some real-time process monitoring. And in that case, you probably want to just work at high field and you just do your PHIP reactions at high field and observe in real time. Other people are interested in highly polarizing a specific molecule. And in that case, I guess sort of a part of a takeaway of this talk is that, I recommend working at low field because it carries certain advantages over ultra low field. Yeah.
Okay. I had a very naive question about the magnetometers you're using. So it's at zero field, Earth magnetic field. And so I guess you cannot put this in between two 1 Tesla permanent magnets, right? Or 0.3.
The magnetometers.
Yes.
Yeah, no, they will saturate. They basically work by you're with those magnetometers, you're measuring essentially electron spins. So if they're in a magnetic field of larger than, I think they typically saturate at something like a few hundred nanotesla. I guess you can go up to maybe a couple of microtesla in some cases with a home-built magnetometer. But you can basically see the problem at like a microtesla field, your electron spins are processing very fast, and you can no longer really polarize them with the laser. So just based on how those magnetometers operate, yeah, they typically saturate at, I guess, microtesla fields.
Okay. And I have a very practical question. So what is the difference, very general about pulses, what is the difference between a slick pulse and like the regular spin lock used in CP?
Yeah, so in a CEP experiment, I don't know exactly how it works. I think a CEP experiment, you're radiating on two spin species, and you're using very strong irradiation. With a slick pulse, I'm not sure if I can answer that so well because I don't know exactly how CP experiments work. These are solid state experiments where you need to you have some very strong spin locking field. And in this case, you're doing a spin lock of just one species, but it's incredibly weak. This slick pulse, you're just applying a transverse field. Okay, so it's in terms of what you're doing in the experiment, it's very similar. But you're choosing a value here of this spin locking field to equilibrate two states in the system. And it turns out because the state energies are different by a J coupling, then this value has to be very, very small. But this is really like this is the same form as just decoupling as well. If you're just applying a strong transverse field to protons, this is a way of decoupling, and that would be basically setting this value nu much larger. So you're disconnecting the states. I don't really know how CP works exactly, so I can't really say much more than that.
Okay, so similar to the spin lock used at high field for CP, these leak pulses are also more or less efficient regarding the B0 inhomogeneities. That's why I saw ramped slick, right? It's to compensate for field inhomogeneities.
Yeah, right. Yeah, exactly. Yeah, because
Okay.
yeah, exactly. So because this is a weak long pulse. So this needs to, you can see the time of this pulse is given by this factor here. So it's like essentially 1 over this chemical shift difference. This is reasonably long normally. This can be tens or hundreds of milliseconds. And that means it's a highly frequency selective pulse. So if there's like a B0 inhomogeneity, that means you have a broad proton line, then you're only irradiating part of it with the slick pulse.
Yes.
And this actually is
Okay.
probably more, so this starts to sound more familiar to people that work with solids, where you're only irradiating part of your line. Maybe I'll take a look at CP afterwards. My guess is that you're doing something very similar with CP, where if you write out the Hamiltonians, you'll see that when you turn on the two fields that essentially spin lock the two different isotopes, you're essentially equilibrating the energies of two states, and you're allowing polarization transfer between them.
Okay, for the sake of time, I will ask one last question over the slide you didn't present. Yasuto, Muda asked you if what was the biggest change when the internal interaction shifted from the J interaction to dipole-dipole interaction?
Yeah, okay. Yeah. So how much time do we have? It's one. Okay. Yeah, I'll just take a couple of minutes to answer this question. Yeah, so what's yeah, so the biggest change when the internal interaction shifts from J interaction to dipole-dipole. Yeah, okay, so right, let me go here. Okay, so so this is something I didn't have time to go through. But the this dipole-dipole interaction is let me show it here. Okay, so this is the idea that we polarize the spins in the sample. And so if all of our spins are highly polarized, then they create a magnetic field. Okay, and that magnetic field is what we're detecting in the coil in any NMR experiment. But if the spins are very highly polarized, the magnetic field becomes so large that it starts to influence the spins in the sample. Okay, so we can, if we calculate, yeah, sorry, it's a little bit, maybe we just look at this sort of calculation down here. So if we have water, and the concentration of that's about 110 molar, in a 9 Tesla magnet, so we have very, very low polarization of the spins, but very high concentration, then the magnetic field we expect from that sample is about 11 nanotesla. That's just from the water spins. So this would cause a line shift of about half a hertz. And this is basically true. You see this if you put water in a high field magnet, you get some small line shift because the water spins are they're at low polarization, but there's enough of them that the magnetic field is appreciable. Well, in hyperpolarization experiments, we're starting to encounter this, but in a more problematic way. So if we're doing PHIP experiments and we produce, okay, our samples are much lower concentration, maybe we have 100 millimolar, but the polarization is significantly higher. We regularly reach tens of % in polarization. So this corresponds to, with taking these numbers, this would be 180 nanotesla field created by the protons. And that causes an 8 hertz line shift. So in the question, what's the biggest change when the internal interaction shifts from J interactions to dipole-dipole interactions? So let me say then, so the J couplings are fixed, but this dipole-dipole term becomes relevant and it acts like an additional magnetic field that the spins sense. And it's really like this. It's because one spin in the sample is sensing the field from all of the other spins around it. So we see in our low field experiments, when we worked with fumarate, we detect, if we just focus on this part here, so this is like the proton resonance at 2 microtesla. Okay, so we have a doublet. We have like 2 peaks in the spectrum. It's 2 microtesla, so the protons are processing at around 85 hertz. If we're working at natural abundance, so we just have 2% carbon labeling in the fumarate, well, we basically see our lines at the expected resonance frequencies, and they basically stay at fixed frequency. But if we use 100% carbon labeling, now the magnetization of the sample is going to be 50 times larger because 50 times more molecules are participating in the hyperpolarization dynamics. And so now we would see this, we see a 3 hertz line shift. We see that the proton line shifted by 3 hertz, and so from that we can calculate that we have a 70 nanotesla internal field in those samples. And then that we basically see this has different effects. It changes the hyperpolarization dynamics. We get this smoothing factor as we're doing our field sweeps when we're working at 100% carbon labeling. Yeah, I think, and I'll just say one last thing, which is Larry Nastagis and the team at Envision published a paper last year in Science Advances where they show this as a real problem. So I won't really say anything about this now, but I'll just point out that what we're showing is that as you increase the concentration of your sample, the polarization that you can create decreases reciprocally. And so basically, because as you increase the concentration of your spins, you're increasing this distant dipolar field amplitude, it decreases the polarization you can generate. So our slick sequences, for example, are they get messed up. And in this paper, they a solution to this problem is shown based on dipolar decoupling. I basically didn't have time to go through that in this talk. Yeah, but that's basically, this is a sort of a very real problem that you encounter when you have these large distant dipolar fields. It actually limits the polarization because you get these large line shifts that affect your pulses that you're trying to apply.